Hello students, welcome to this lecture. This is going to be the first unit of electrical machines to the synchronous generators. So in this is the syllabus of this particular unit. In these topics, we are going to see about the construction details and the types of the rotors of the synchronous generators. So normally these synchronous generators are coming under the main category of AC machines, and the AC machines are going to be segregated into two main categories like synchronous machines and the asynchronous machines. The asynchronous machines are going to be induction machines. The synchronous machines are classified into synchronous content generators and the synchronous motors, and the asynchronous machines are going to be classified into induction generators and the induction motors. The synchronous generators are going to be the main primary source of the electrical energy of the main power systems. The power systems are going to be basically as the AC transmission systems in all over the world, because the AC transmission systems having very higher advantages over the DC transmission systems, as the I square R losses are going to be very less. So the main primary source of electrical energy will be the AC energy, AC power supply that is produced by these kind of synchronous generators. The synchronous motors are going to be used as motors as well as the power factor compensators. So as we are going to see about these kind of motors in the unit number 2, and the motors are going to be constant speed in nature, and they may be supplied with the many industrial applications, and they can be used as a power factor compensator in the large power systems, and they are going to be named as synchronous condensers. And as the other hand, the asynchronous machines, that are these induction machines, will be having the first subclassification as induction generators. And induction generators are going to be have a lack of separate field excitation, so that the induction machines will be having the speed of less than the synchronous speed, and these kind of machines will be having AC supply for the rotors, so that they won't touch to the synchronous speed. And the induction generators are since the induction generators having lack of separate field excitation, they can be used rarely used as the generators, but the ruggedness and the variable supply nature of the induction generators, these induction generators are going to be used with the wind generators, because the wind speed are going to be varied depending upon the time. So the induction generators can be used on those applications. Induction motors are going to be most widely used electrical motors in both domestic and industrial applications. The synchronous generators having the types as according to the arrangement of the field and the armature windings. First, as a stationary armature and the rotating field. Since the synchronous machine is going to working under the principle of electromagnetic induction, but the arrangement of the coils are going to be somewhat different, because the as we have said that synchronous machines will be having the three-phase output, and in order to having that three-phase output, we will be supplied with the field of DC field windings. So the DC field windings will be supplying to the field. So if either the field is going to be rotatory, or the stator is or the three-phase winding may be rotatory. So in either case, the DC field windings will be supplying a magnetic field, which is going to be cut those three-phase windings, and they will be supplied with the EMFs, which are going to be displaced in space and in time with 120 degrees displacement. So for this displacement only, the three-phase windings are going to be wound. So by that displacement, the displacement of 120 degree may be supplied with the supply voltage of the output of the synchronous generators. So in order to get that particular output, we can have these two types of arrangement. One as a stationary armature with a rotating field, and another one will be the stationary field with the rotating armature. So the first case will be for the above 5 kVA, and the second case for the below 5 kVA, because the above 5 kVA machines are going to be heavier in nature, so that the armature stationary winding will be supplied with the three phase, and the rotating field will be the DC winding. And here, since these machines are going to be very small, so the stationary field winding, that is the stationary DC field winding, will be on the stator, and the three-phase output will be on the rotor. So advantage of having the stationary armature, that is the stationary three-phase winding, and the rotating DC field winding, is comes as the high voltage AC winding and its insulation not subjected to the centrifugal forces. So since the AC windings are not going to be subjected into the centrifugal forces, we can have the better insulation over the AC windings, because they are all going to be high voltage in nature, from 11 kV to the 33 kV. So we can have the better insulation, easier to collect the larger current from the stationary members. So this is obvious when larger current are going to be subjected, the stationary member is going to be easier option. The third thing will be the rotating field makes the overall construction as simple as possible. The fourth will be the problem of sparking and the slip ring may be avoided, and the ventilation arrangement for the HV can be improved, because the sparking and the ventilation are going to be the very much problematic for the for having the rotatory three-phase windings. So that can be avoided if we are having the stationary armature three-phase windings. The LV DC excitation easily supplied through the slip rings and the brushes to the rotor field windings. That is also obvious, and the noiseless running is possible, because since we are having very less weight in the rotor side due to the DC field winding on the rotor, we may be it may be possible that the noiseless operation. And since the air gap is going to be very less and they are going to be uniform in case of cylindrical rotor, and in case of salient pole rotor too, the air gap may be somewhat uniform, because the air gap is going to be very less in comparing to the stationary field winding or the rotating armature, and the better mechanical balancing of the rotor in case of rotating fields. The construction of the alternator with the stationary armature and the rotating field, the stator will be having a sheet of steel lamination core stampings with the slots arranged like we have in this particular diagram. So here the stator cores are going to be supplied with the slots So these slots may be open or closed in nature depending upon the voltage values which for which the stator is going to be designed. So these particular slots are going to be arranged, and they are going to be designed for a given voltage rating or the power rating of the machine. So we may be designed with these stampings, and these stampings are going to be collected and they are going to be riveted, and the arrangement of this particular stampings are going to be fixed on the periphery of the stator. As this particular armature winding can be three phase, so they can be connected with the star arrangement. So this is the stator arrangement. So here the stator steel housing on the yoke of the machine, and the particular stampings are going to be placed on onto the laminated iron core with the slots over inside this particular steel housing. So these are all the stator details. Here we have the slots as blue marked. So on those blue marked, we will be having the coils to be placed, and the end of the coils are going to be connected together. They can be connected with the outer rings with the end windings, and these particular end windings are connected, and they will be supplied with the three-phase output of this particular machine. And these are all the very clear idea of this particular placing of the coils, and the number of coils, number of particular slats, and the distances of these particular coils can be calculated and can be designed, and these kind of details will be discussed in the next video. The rotors will be having two types in nature. One is salient pole rotor, that is the projected poles, and the another one is going to be non-salient pole, non-projected. So the salient pole projected poles will be uh, mounted on the largest circular frames, and since the projector poles are going to be mounted in separate, and they will be fixed on to the particular larger circular frames, so the rotor will be having very great weight. So the since these are all going to be in great weight, the larger diameter, and these kind of rotors will be having short axle length. Since the weight of the rotor is very enormous, these kind of rotors are going to be used with the hydraulic turbines, and the speed that is being supplied with this kind of heavier projector pole rotors, uh, speed will be varied from 120 rpm to the 500 rpm. And the main speed criteria that can be met out by this particular projector pole rotor type machines, the damper windings are going to be used. So the damper windings are the copper bars which are placed on the top of the uh, projector poles. So on the top of the projector poles, we will be putting some of the holes. So these holes are going to be connected with the copper bars. So those copper bars are going to be short circuited. So whenever this particular rotor will be going out of the synchronous speed, the eddy currents will be formed inside these particular copper bars, so that the rotor will be going in closer to the synchronous speed, so that the speed of the machine can be maintained at the synchronous speed. And also, for in order to prevent the hunting, that is the uh, going out of the synchronous speed is going to be called as the hunting. So in order to prevent this hunting, we will be supplied with this kind of damper windings, and the EMF generator will be the sinusoidal. So for that purpose also the damper windings will be used. And the next type will be the non-salient pole type. So for non-salient pole type, rotors will be as as similar to the induction machines rotors. So these rotors will be having the slots as equal to the rotor slots. So this kind of rotor slots will be supplied with the windings, and the DC field will be given to this particular rotor windings. So since this particular cylindrical rotor having the very smooth air gap length, so these are all going to be the smooth cylindrical rotors, and these can be operated with the higher speeds, so that these particular rotors can be driven by the uh, steam turbines. So since these are all going to be very less in weight, and these kind of rotors can be designed with the smaller diameter and the larger axial lengths, so that the windage losses will be less, and the speed can be obtained from the 1200 rpm to the 3000 rpm, and better balancing will be maintained. And since these are all going to be very smaller in diameter and greater axial length, they can be used with the noiseless, and the flux distribution will be nearly sinusoidal. Since the speed of the machine is going to be synchronous speed, the synchronous speed may be varied depending upon the poles. So the synchronous speed can be calculated from the 120f divided by p. The frequency of the operation will be 50 Hz, so that is going to be common, and the number of poles uh, will be maintained for the given synchronous speed. So the poles are going to be um, even in nature, 2 4 6, and the speeds can be likewise. So the 4 poles 1500 rpm machines are going to be common in all the applications. Thank you.